Hello, it's Keith from Kinvert, and in this video I'm going to be going over some interest rate problems. We want to compare three different things, so I know this is wishful thinking, but imagine you can find some sort of bank account that's going to get you an annual return of 6.5% compounding monthly versus 6.2% compounding daily versus 6% which compounds continuously, right? Like beyond every second, it continuously compounds. All right, how will these end up comparing? Which one is the best? For the sake of argument, we don't really need a principal, but we can just make the principal be $1,000, just for a somewhat round number. Let's just begin with these. So the first one is 6.5% monthly. So let's look at this. We've got A, which we don't know. A is P, which we're going to treat as 1,000. So this is just what we start off with. And this is times 1 plus R over N. Now let's take a look at that to the NT. So R is the annual rate. Now note that this is in decimal form. This is not a percent. Okay, or you're going to end up being way off. A decimal form. N is the number of periods per year. So if it's monthly, N would be, I hope you realize, 12. If it's daily, we'll assume it's not a leap year or something. That's going to be 365 for N in that case. Continuously, it'd basically be infinity, but we're not going to be doing that. We use a different form of the equation for that. So 1 plus R over N, all of that, 1 plus R over the N, that goes to the NT. N is the number of periods per year, once again, and T is the number of years. Okay, in this case, it's going to be 4 years. So let's go ahead and write this out with the numbers in there. I think that'd make more sense. 1 plus R. R is the annual rate. 0.0. Hopefully you can see the decimal. 6.5. And that is divided by the number of periods per year. That's going to be 12. And then this goes to the NT. Number of periods per year. This is 12 times T is 4, and we can go ahead and calculate this out. I'm going to go ahead and do that now. We've got don't forget your parentheses and stuff if you're putting this in a calculator. It's important to have your parentheses correct as I am showing them here. Over 12 to the 48, which is the 12 times 4. So for this one, right here, we end up with $1,296.02. All right, let's do the same thing for the 6.2, and I'll just go kind of more yellow, I guess, for this one. We have A is, once again, 1,000 times 1 plus 0.062 over 12, not 12, over 365. 365, and this goes to the 365 times 4. Now if you're putting this to the power of something, you're going to, because the 48's an easy one. This one you might need to multiply out. So I'm going to go back to here at 6.2%. We are compounding 365 times, and so we end up with 365 times 4 there, and our total is 1,281.43. Okay, and so this is worse off. You would be worse off taking this versus the other. It's a lower interest rate, and the amount of compounding does not really help. Now, what I can quick do is take this and change it back to the 6.5%. With the better compounding, this would have earned you another 88 cents. Had this compounded daily instead of monthly. But that wasn't the term, so we're not going to go over that. And then finally, we've got, let's go with pretty green, I guess. We've got this last one, the 6% compounding continuously. So we need a different equation for this. Same terms, P is the principal, it's what you begin with. E is approximately like 2.72 or something like that. Let me double check it. This is embarrassing. It's probably my, 2.718. So if I'm in a hurry, I just do 2.72. Engineers sometimes get mocked for using approximate numbers. In my calculator, I use the exact one. So we've got, let's see, P is 1,000 in this case. 1,000 times E, hopefully that's in your calculator, to the RT. R is the annual rate, so we have 0.06 times T, which is 4. And if you're doing, make sure you got your parentheses correct. So I've got 1,000 E to the 0.06 times 4. And what I ended up with for the continuous compounding is 1271.25. And again, let's try this quick at a 6.5%. This would have been 1296.93. This would have gotten you 93 cents versus this one's 90 cents. So this would have been 3 cents better if all things being equal, if the interest rates were all the same. But in the end, the best deal is this one here. Now, it's different if you're looking at mortgages, right? You want a low interest rate. But if you can somehow magically find a place that'll get you 6.5% annual interest, that's pretty good. This would be the best deal. So the 6.5% monthly is the best deal in this case. You kind of wouldn't have needed to know the equations or do the math if these were all at the same interest rate, because the more it compounds, the higher you're going to end up with your amount. But since they were all different interest rates, we wanted to calculate this out. So remember that this is one where you've got like an integer number of terms, of periods that this compounds over a year. This one is when it is kind of an infinite number of compounding. Okay, this is where you're going to use E to calculate that. So this is Keith from Kinvert. This is part of our online course for Pre Calculus and Algebra. We went over some interest rate problems, particularly how to compare 3 different things that you have with different interest rates and different compounding schedules. I hope you guys found this helpful, and we will see you in the next one. Bye-bye.